Hi everyone, welcome to part 2 of chapter 5. Today we're going to continue our talk on gases. We are going to look a little more at gas properties as well as calculations that we can do with the gases. So a really useful condition in chemistry is standard conditions. And we use standard conditions because the volume of a gas can vary with pressure and temperature. We want to have some agreed upon set of conditions to report our measurements so that comparisons are really easy across different labs. So we call these conditions standard conditions, or STP. And STP stands for standard temperature and pressure. So our standard pressure is 1 atmosphere, or anything that it happens to be equal to, like 760 millimeters of mercury, or any of those other conversions that we saw in the previous lecture. Standard temperature is 273 Kelvin, or 0 degrees Celsius, because those mean the same thing. Typically in chemistry, or in gases, we will use 273 Kelvin, because most times we need our temperature in Kelvin. So let's look at a combined gas law problem that uses this standard temperature and pressure. So it says a gas occupies 10 liters at 44.1 psi and 27 degrees Celsius. What volume will it occupy at standard conditions? So again, we're always going to start off with our variables. And we know that this is a combined gas law problem because it's talking about changing conditions, right? We're starting at one set of conditions and we're going to change to another set of conditions. So we have our initial volume is 10 liters. We have 44.1 psi, and we have 27 degrees Celsius, but we can't use this in Celsius, so we're always going to convert it to Kelvin. So we'll add 273, and that gives us 300 Kelvin. And I'm going to put 300 point Kelvin here to show that I need 3 significant figures. So it says standard conditions, so that means STP, okay? So our STP, that would be 1 atm, but we can't use this in atmospheres because our initial pressure is in psi. So you could convert that, to psi, you could convert your initial pressure to atmospheres if you like, or you can just use P2 in your standard conditions. So 1 atmosphere is the same as 14.7 psi. You didn't need to have this one memorized. I would give this to you. So 14.7 psi, that's the same as 1 atmosphere, and it's asking what volume, so we don't know that. And our temperature is always going to be 0 degrees Celsius or 273 Kelvin. So we can set this up, P1 V1 over T1 equals P2 V2 over T2. So you can arrange this a couple different ways. I'm going to go ahead and just cross multiply here. So that gives us P1 V1 T2 over, equals P2 V2 T1. And now, if we're going to go ahead and rearrange for V2, we're going to divide both sides by P2 T1 to get rid of the P2 and the T1 on this side so that V2 is by itself. So we get V2 equals P1 V1 T2 over P2 T1. Okay, so we can plug things in. P1 is 44.1 psi. V1 is 10.0 liters. T2 is 273 Kelvin. We have P2 as 14.7 psi. And T1 as 300 point Kelvin. And then you can go ahead and multiply the top, divide the bottom. Make sure you're consistent with your significant figures. And for this answer, you will get 27.3 liters. Okay. So that would be how we would solve a problem using STP. STP tells you a pressure and a temperature, and we can use that to find a volume at a new set of conditions. So another gas law that we are going to look at is Avogadro's law. We've already talked a little bit about Avogadro when we talked about Avogadro's number when we were dealing with moles, right? We said that, Avogadro said that there were 6.022 times 10 to the 23rd particles in 1 mole of a substance, okay? He also came up, though, with the molar volume and the fact that volume is directly proportional to the number of gas molecules. So at a given, at a constant pressure and temperature, so we're not changing pressure, we're not changing temperature, our volume versus our number of moles will be a constant, which means that as we increase our number of gas particles, our volume will go up. As we decrease our number of gas particles, our volume will go down. And this makes sense, right? If we have more gas particles, then, as we, add more gas particles, we're going to get more collisions with the walls of the container. More collisions means more pressure, and if our container is expandable, as we get more pressure, that container will expand like a balloon until our internal pressure equals our outside pressure. And so we'll get a larger volume. So more particles means more collisions, means more pressure, means our balloon expands. And the opposite is also true, right? If we had fewer gas particles, then we would have less collisions, which would mean less pressure, which would mean our balloon would shrink. So we will always count our number of gas particles by moles. This N, right? N is going to stand for number of moles. Okay, because we're not going to go through and count individual gas particles. That would be ridiculous. One thing to note is that at STP, if we have equal volumes of gases, they will contain the same number of molecules. That was what Avogadro is really known for, the molar volume of gases, which is really, really cool. The type of gas doesn't matter. It just matters how many particles are in there, the number of moles of your particles. So if we have the equal volume of two gases, then they will have the same number of particles, but only at STP. Okay? So here's his relationship. Our number, V1 over N1 equals V2 over N2, because our V over N is going to be a constant. So we can set one set of conditions before equal to the set of conditions after. Okay? So here's his law. As we increase the number of moles of our particles, we are increasing our volume. Okay? So V1 over N1 equals V2 over N2. So Avogadro's law states that our gas volume and our pressure depend only on the number of moles present, not on what our gas is. So we're just going to look at number of moles, right, to tell us our pressure. And if if our container can expand, then we will look at our volume. Okay, and people will often ask, well, shouldn't 1 mole of larger molecules occupy more space than 1 of the small moles of smaller molecules? Well, no, because remember, at the beginning, we were looking at kinetic molecular theory, and we stated that since, our gas particles themselves are so small, we are going to assume that they essentially have no volume. Okay, they're so small compared with the amount of space in between the gas particles that it doesn't matter. So 1 mole of larger molecules will occupy the same amount of space as 1 mole of smaller molecules because the gas particles themselves are so small. Similarly, people will ask, well, why doesn't 1 mole of heavier molecules exert more pressure than 1 mole of lighter molecules? Well, again, when we're looking at pressure, we're just looking at collisions. We're looking at number of collisions. And so, our 1 mole of our gas particles, our heavy ones, will have the same number of collisions as our lighter ones. So since we're just looking at collisions here, we are, going to have that same pressure. So here we go. This is what it looks like when we're just looking at our number of particles. Say we have, a condition where we have some gas, and our gas, is an expandable container. So that means our pressure inside of our gas is equal to our atmospheric pressure. If we go through and we pump in more gas particles, and we have a fixed temperature, as we put more particles in, that means we're going to have more collisions. And when we have more collisions, that's going to build up pressure inside of our gas, right? And so when we build up pressure, if we have a container that can expand, then our volume will increase to make room for that gas, to alleviate that pressure, right? So these gas particles, because there's increased pressure in here, they will push up on this piston and cause it to expand until the internal pressure equals the external pressure. Our pressure inside of our gas equals the outside. So again, this is directly related to the number of particles. When we increase the number of particles, then we are going to increase the pressure of our gas, and if it can expand, it will increase the volume. about another gas law called the ideal gas law. And by combining all of these gas laws we've talked about before, we can kind of write a general equation. The only other new variable that we are going to use is this value for R, and R is called the gas constant. The value for R depends on the units of pressure and volume. So in order to just use one value for R in this class, we are always going to convert our units of pressure to atmospheres and volume to liters. And this is just for the ideal gas law. The combined gas law, you can use other units. You could use milliliters, or you can use millimeters of mercury, as long as you're being consistent. But here, because we're going to use this value for R, 0.08206 atmospheres liters over moles Kelvin, we're always going to need to use atmospheres and liters. If you were to use other units, you would have to use a different value for R. Okay, so the cool thing about the ideal gas law is it allows us to find one of the variables if we know the other three. And so here is our equation. So we have PV equals nRT, or PIV-NERT as we like to call it. So our pressure is always going to be in atmospheres. Our volume is going to be in liters. N is going to be the number of moles of our gas. R is the gas law constant. And temperature, like before, always has to be in Kelvin. So if you know, say you knew pressure, volume, and number of moles, you could use it to find temperature. Or, if you knew, volume, number of moles, and temperature, you could use it to find pressure. So this will always be at one set of conditions. We'll use the combined gas law when our gas conditions are changing. We will use the ideal gas law when we just have one set of conditions. So here's an example. Dinitrogen monoxide, or laughing gas, is used by dentists as an anesthetic. If 2.86 moles of a gas occupies 20-liter tank at 23 degrees Celsius, what is the pressure in millimeters of mercury in the tank at the dentist's office? Okay, so here we just have, moles of gas. We just have one volume, one temperature. We're looking for one pressure, right? So we don't have changing conditions. These are set conditions. So that means we're going to use PV equals nRT for this problem. So we have P, V, N, R, and T that we're using. So our pressure is what we're trying to find. Our volume is 20.0 liters. We have 2.86 moles of our gas. Our R value is 0.08206 liters atmospheres over moles Kelvin. And our temperature is 23 degrees Celsius, but we can't use it as Celsius. So we'll add 273. That gets us 296 Kelvin. Okay, so now we have, PV equals nRT. We can divide both sides by our volume to get our pressure by itself. And so then we get pressure equals nRT over V. And then we can just plug in our values. All over our volume, and then make sure to round for sig figs and you will get your answer. So again, we will use this ideal gas law, this PIV-NERT equation, anytime we just have one set of conditions, and we'll use our combined gas law anytime we have changing conditions. So the molar volume, right, like we were talking about before, with Avogadro's law, if we have a set number of particles at a given temperature and pressure, then they will always have the same volume. And so if we solve this ideal gas law for the volume of 1 mole of a gas, any gas, at STP, it will always be 22.4 liters. Okay, so this will be for 6.02 times 10 to the 23rd molecules of a gas. Right? But again, it doesn't matter what the gas is, as long as you have 1 mole of a gas at STP, it is always going to be 22.4 liters. So we call this the molar volume. And just as a reminder, even though it's all the same, 1 mole of a gas, that 1 mole of a gas may have different masses. Okay? If it's at STP and we have 1 mole, It will have a set volume, but it will have a different mass because they are different gases. So be careful there. Okay, they have the same volume, same number of moles, but a different mass. So here it is, if we have helium, xenon, or methane, right, we have 1 mole of each one of them at STP. They are all going to be 22.4 liters. Okay, so it doesn't matter what the gas is, they're always going to be 22.4 liters, but they will have a different mass. They will have the same volume, different mass. So we can use this molar volume to go about doing some stoichiometry, right? So we've learned how to convert our volume of a gas into moles of a gas, and then we can use our mole ratio to convert that into moles of, something else. And then we can convert, into volume or, grams or whatever the case may be. But now we can use this to do stoichiometry. So let's go ahead and do an example. So this says, how many liters of oxygen at STP can be made from the decomposition of 100 grams of lead-4 oxide? Okay, and the important thing here is that this is at STP. And when it's at STP, then we can use this 1 mole equals 22.4 liters. But I want you to be very, very, very careful. You can only use this relationship if you are at STP. And I will show you how to do this calculation if you're not STP in the next example. So we're going to always start with what we're given. So we'll start with 100 grams of lead-4 oxide. Okay, so now we will convert our lead oxide into moles of lead oxide, and we'll do that using the molar mass. So we have 293.2 grams of lead oxide for every 1 mole of lead oxide, lead-4 oxide. Okay, and now that we've converted into our lead-4 oxide, right, our moles, we can use our mole ratio now to convert into moles of oxygen. For every 2 moles of lead-4 oxygen, we have 1 mole of oxygen gas. So we have 2 moles of our lead-4 oxide, 1 mole of O2. And again, since this is at STP, we can use this conversion factor. 1 mole of our oxygen is equal to 22.4 liters of oxygen. So again, moles has to cancel moles, so we'll use 1 mole down here. 1 mole of our oxygen is equal to 22.4 liters of oxygen. And then we can go through, make sure all your units cancel, grams cancels grams, moles cancels moles, moles cancels moles, and we're left with liters of oxygen, which is what we were trying to find. So we can multiply that out, and we will get 3.82 liters of oxygen gas. Okay, but again, we can only do this last step because we are at STP. Okay, so then you'll be like, okay, well, what if we are not at STP? All right, so if you're not at STP, this is what we will do. And the way that we recognize that it's not STP is that we are given a pressure and a temperature that is not STP, right? Remember, one atmosphere and 273 Kelvin is STP. So if you have anything different from that, you cannot use that 1 mole equals 22.4 liters. So let's try this example. We're looking for a volume of oxygen that's generated by thermolysis of 10 grams of mercuric oxide. So we have our starting material, and we can convert that, right? Our grams, we can turn our grams into moles using the molar mass. So 216.59, and that will give us 1 mole. And then we can use the relationship, right, our mole ratio from our balanced chemical equation. We know for every 2 moles of our mercuric oxide, we are making 1 mole of O2. So now we cannot use that we cannot use that 22.4 liters because we are not at STP. So we have to stop here. Okay, we will just convert to moles and stop. So we get out of this, we get 0.0231 moles of O2. And the way that we will go about finding our volume is we will use Pivnert. Okay, so if we're not at STP, we have to stop our train tracks at moles and use Pivnert to figure out our volume. So we have P, V, N, R, and T. Okay, so our pressure is 0.750 ATMs. Our volume is what we're trying to find. We have our number of moles, 0.0231. R is always a constant, 0.08206. And we have 313 Kelvin. So we have PV equals nRT. We will rearrange to solve for our volume, so we'll divide pressure by both sides. Okay, so we get volume is equal to nRT over P. So volume is equal to, and we can plug in all of our variables now. So 0.0231 moles. We have R is 0.08206 liters atmospheres over moles Kelvin. And then our temperature is 313 Kelvin. And we're dividing all of that by our pressure, which is 0.750 atms. So that will get us that our volume is equal to 0.791 liters of O2. So again, we have to solve it this way because we were not at STP. So if we are at STP, we can use the 1 mole equals 22.4 liters. Makes it a much simpler problem. We can just make a train track and be done with it. If we are not at STP, then we need to use our train track, our dimensional analysis to get to moles of oxygen or moles of whatever our gas is, and then we'll use Pivnert to find our volume. Okay, so be very, very careful. Only use 22.4 liters at STP. The last topic we are going to talk about today is density. Density is the ratio of mass over volume. So we have density equals m over v. And when we're talking about this with respect to, liquids and solids, we will use grams per milliliter. But the density of gases, because those particles are so light and so far apart, we will typically give those densities in grams per liter. By using information like the mass of 1 mole is equal to the molar mass, and the mass, and the volume of 1 mole at STP is 22.4 liters, we can actually get a new equation that we can use the density is equal to the molar mass in grams over 22.4 liters. Because the units for these normally would use the molar mass in grams per mole and our molar volume in liters per mole, and those mole units will cancel out when we divide them, and we will get grams per liters. But again, this is only going to be true at STP. So at STP, we can use the density is equal to the molar mass over 22.4 liters. So let's go ahead and see an example problem. So calculate the density of nitrogen gas at STP. So again, we have our equation. Density is equal to the molar mass over 22.4 liters. So the only thing we need to solve this problem is to find the molar mass of nitrogen gas. So we have the density is going to be equal to 28.02 grams over our 22.4 liters. When we divide that up, we get 1.25 grams per liter for our density of nitrogen. Again, at STP. We can only use this equation if we are at STP. So the way that we will calculate density not at STP is we will use this equation, density equals MP over RT, where our M is molar mass, that's in grams per mole. Our pressure is in atmospheres. Our R is in liters atmospheres over moles Kelvin, right? That'll be that same R that we were using earlier, the ideal gas law constant. And our T is in our temperature, which will always need to be in Kelvin. And so when we go ahead and we cancel out all of the units, we'll get our density in grams per liter. So again, we'll use this when we are not at STP. So it says calculate the density of nitrogen at 125 degrees Celsius and 755 millimeters of mercury. So again, we need to change our temperature to Kelvin. So we'll add 273, and that gets us 398 Kelvin. And then we will convert our millimeters of mercury to atmospheres by dividing by 760, and that will get us 0.993 atms. So then when we can plug this into our equation, so density equals our molar mass in grams per mole, so that's 28.02 grams per mole, multiplied by our pressure in atmosphere, 0.993 atms, over, and we have our R value, 0.08206 liters atmospheres over moles Kelvin, times our temperature, and that is in Kelvin, and that's 398 Kelvin. So if we look at our units here, right, we have moles cancels moles, atmospheres cancels atmospheres, and we have our kelvins that are canceling, so we'll end up with grams per liter as our unit. Okay, so if we multiply and divide all this out, we will get 0.852 grams per liter. So it is much less dense at this temperature because as our temperature increases, our gas particles are moving faster. They tend to move a little bit farther apart. So there we go. That is how we use this equation. This equation, just so you know, is kind of a play off of PIVNART, PV equals nRT. That's why we're using our gas law equation. We've just kind of subbed out this N value for the molar mass so that we can solve for grams per liter instead of solving for moles. So let's try another one. Calculate the density of a gas at 755 torr and 27 degrees Celsius if 0.250 moles weighs 9.988 grams. So rather than giving us the molar mass, they've given us grams and moles. But we can calculate the molar mass because we know molar mass is grams per mole. So if instead we just calculate this as grams divided by moles. And that will allow us to get our molar mass in grams per mole, and we will get 40.0 grams per mole. So now we'll do the exact same thing we did last time. We have density equals MP over RT. So our molar mass is 40.0 grams per mole times our pressure, and so here again we have our pressure is in torr. We need to divide that by 760, and that will get us 1.02 ATMs. So we have 1.02 atmospheres over our R value, 0.08206 liters atmospheres over moles Kelvin. And then we have our temperature, and so we have 27 degrees Celsius, so again we need to add 273. And that will get us 300 Kelvin. So then we can just multiply and divide all of that out. We will get 1.66 grams per liter. This gas is much more dense than our nitrogen was, and that's because we have a larger molar mass here. Usually that will correspond to a more dense gas because our value on the top here, that grams value, will be a little bit larger. So the only difference between this problem and the last one is that we had an unknown gas, but instead they give us grams and moles, so we could calculate the molar mass before plugging it into this equation. And that is the end of this set of slides. Keep working on that Chapter 5 lecture worksheet, and remember that there are also more practice problems on your study guides. As always, if you have any questions, please send them to me, and I will talk to you guys next time.